Well, hello everyone. Welcome to the AIPG Lunch and Earn webinar for October. I'm Aaron Johnson. I'm the Executive Director of the American Institute of Professional Geologists, and it's my pleasure to welcome you today. A couple of quick announcements. First, if you need a certificate for completion of CEUs for this webinar, that will come to the email address that you use to register for the webinar, so watch your email for that. If you don't get that within the next 24 hours or so, please reach out to us and we'll be sure to try to get that certificate to you. Secondly, a couple announcements regarding continuing education for New York. If you are requiring these CEUs for your registration in New York, the New York State Education Department requires that you complete an assessment quiz to meet the requirements for continuing education in New York. In addition, the New York State Education Department requires that any hour of continuing education include 50 minutes of instructional time. So please remain on for the question and answer session. If you don't stay on for the full 50 minutes, we can't issue that certificate. That is a requirement of the New York State Education Department. Well, today it is my pleasure to welcome Dr. Bill Harrison. Bill is going to talk to us today about Michigan potash. He did a bachelor's and master's at the University of South Florida, went on and got a PhD at Cincinnati, so he's a Bearcat. He's got 4 decades of experience in studying Michigan geology, has published broadly in sedimentology, stratigraphy, and petroleum geology in Michigan, and has supervised literally dozens of graduate students who are pursuing advanced education in geology. Currently, he is the principal research scientist and the research director of the Michigan Geological Repository for Research and Education, which is part of the Michigan Geological Survey, which is housed there at Western Michigan. Bill, I truly do thank you for sharing your time and expertise with us today. I look forward to learning more about potash deposits in Michigan. The floor is yours.
Thanks, Aaron. I really appreciate that. It's great to have everybody on today, and thank you so much for tuning in. Hope I can give you a little bit of information about an interesting geological deposit here in the state of Michigan. It's a natural resource, but we feel like it's been a little bit overlooked. And with our emphasis these days nationwide on critical minerals, one of those is the element potassium or potash, and that's something that all the farmers know about and lots of folks are interested in these days. So let's find out what we can do about it here in Michigan. Before we get started too much, I thought I'd just give everybody, in case you weren't too familiar with potash as a commodity. It is a commodity. It's traded nationally and internationally, and it's a material that's mined out of the earth, and it's a natural mineral element. The concept of potash itself is typically talked about as a potassium oxide, or K2O is the conventional way of expressing that. It actually represents a group of mineral types. There's several different minerals that are contain potash in the earth. The most common one is potassium chloride. It's a salt. The mineral name is sylvite. You may be familiar with halite as sodium chloride, common table salt. If you evaporate seawater enough, you can get that table salt, and that's what sea salt is if you go to the store and buy a little expensive bottle of sea salt. Potassium chloride is also a sea salt, and it precipitates pretty much after all of the sodium chloride that's in seawater has already been precipitated out. So it's a highly evaporative type of substance and only occurs in a few places around the world, but they're all in these highly evaporitic salt basins. In terms of a commodity, these are the most recent statistics that I could find out there from the U.S. Geological Survey. In 2024, the United States produced domestically around 420,000 tons of potash. That has a pretty good value. It's a quite valuable commodity these days at a little over $1,200 a ton. However, Here's the story about the critical minerals issue, that we import something like 96% of all the potash that we use. So for all the farmers that are mixing potash or potassium into their fertilizers, almost all of that's coming from somewhere else besides within the United States. There's a number of places in the world. The world's largest producer is Canada and Western Canada, particularly Saskatchewan. They produce enormous amounts of potash, and it's mostly coming from underground mines. Russia and Belarus are also major producers, and there have been some geopolitical concerns about those in recent years, and that's had a huge impact on the world price. In the United States, there are really only 3 known commercial producing areas. Until 2013, the state of Michigan had a small commercial mining operation in the north central part of the state, but it was actually managed by a Canadian company. Also, the states of New Mexico and Utah have commercial production, and most of that production, pretty much all of the present day commercial production, is coming out of the New Mexico mines. So why do we care about potash as a particular mineral, critical mineral? As I mentioned, it's a component in fertilizer. If you look at your bag of fertilizer, you'll see 3 numbers on there. In this case, 26-2-11. The 26 stands for nitrogen, the 2 stands for phosphorus, and the 11 stands for potassium. So these are the 3 major elements that occur in fertilizer, and they're absolutely crucial components for any kind of vegetative growth, plant growth. Plants can't really survive without them. And particularly in the case of potassium, it helps the plant move water through its system. Typically, if you are buying fertilizer that has potassium in it, you'll see it like you see in those 2 glass vials. It's some sort of granular crystalline material. The cleaner, the whiter it is, the more transparent it is, the purer the form. The one on the left is pretty dark. It has quite a bit of impurities, several percent probably, in terms of iron oxide, in terms of clay minerals. And so that's a little bit of a negative in terms of the quality of that product. The map there of the United States is from a few years ago, U.S. Geological Survey. This is where the demand for potash occurs, typically around the United States. The 3 black and red boxes are the locations of the 3 commercial potash producing areas. The one in Michigan is no longer commercially active, but the New Mexico and Utah ones are located out there in the western part of the U.S. As I mentioned, in Canada, they mine this as underground mining, hundreds to thousands of feet below the surface. In Michigan, the Mosaic Corporation, which is a Canadian company, did run a potash mining operation near the town of Hershey up in the north central part of the state of Michigan. And this is all done by solution mining. Basically, they drill a couple of wells. One well, water is injected into that well. It goes down to the salt formation, circulates through the salt formation. You eventually create a cavern by dissolving out that salt, and then the brine is pumped back to the surface, and those 2 domal structures are crystallizers where they, in this case, they were using natural gas to evaporate the water. The water is actually recaptured and recycled, so it's a closed system in terms of the water utilization. One of the crystallizers was to produce common salt, sodium chloride salt, and the other one was for the potash. As you continue to evaporate water, the first salts that would come out would be the sodium chloride salts, and then as time passes and you remove all the sodium chloride, you will eventually start producing potassium chloride. So the Michigan operation is especially a solution mining operation rather than underground mining. So from the geology standpoint, the Michigan Basin it's a large intercratonic basin. Sedimentary rocks over 15,000 feet in thickness, so it's a thick, pretty deep basin. During the Silurian time, there was a lot of evaporation. The part of Michigan was near the equator, and if you get some restriction into the basin, then you can start evaporating the seawater that's in there. And over time, large, thick deposits of salt get formed. In fact, through this Silurian salina group, there's over 3,000 feet of mixed evaporite deposits, including halite and sylvite. The sylvite beds only occur in the lowest of all of these formations. That is the oldest. It's called the Salina A1 salt formation. And it occurs mostly only in the deepest parts of the Michigan Basin, especially located toward the north central portion of the state. The depths to the top of that formation range from around 7,000 to over 9,000 feet in depth. So you can understand why you could only do this by solution mining processes. I'll show you a map in a few minutes, but this deposit does occur in a fairly widespread area. We've been able to detect at least traces of the potash in the salt formation in about 17 counties. So it's a pretty broad area in the northern half of the state. Probably in terms of actual commercial quantities, only about half of that area is going to really be available because of the thickness and the quality of the potash deposits. If you look for Michigan stratigraphy or geology, you'll find this chart. It's from a few years ago that we put together, showing all the different geologic formations in the state, and that stratigraphic column or that geologic columns in the deepest parts of the basin over 15,000 feet in thickness. The salt formations, and particularly the potash, are about halfway down through that column, somewhere around 700 to 7,500 feet thick. Just in terms of reference, most geoscientists understand the Grand Canyon. That's one of our great landmarks here in the country. And from the top of the Kaibab Plateau down to the river is about 5,000 feet. So this potash and these wells that are drilled to mine it are at about 1.5 times as deep as the Grand Canyon is. So back in the Silurian, a lot of people have studied, Michigan's a big oil and gas producing state as well as other types of minerals. So in terms of the basic paleogeography, people have put that data together pretty good. And a fellow named Dan Gill back in the 70s produced a really nice paleogeographic map showing the distribution of different kinds of sedimentary environments that existed across the state of Michigan during that part of time. And one of the things that was going on was we were in a tropical setting and there was lots of reef growth. So what happened was the Michigan Basin's always been constantly subsiding in terms of a structural part of the Earth's crust. And so there was in the center of the state, there was a deep basin that was forming, but around the edges, we got lots of development of carbonate platforms and reef tracks and reef banks. And it actually grew up to the point where it was just about at sea level. And then anytime you would have a little bit of fluctuation in sea level during some climatic changes or something, and global sea level went down a little bit, you would actually restrict the basin. And there were a few openings that we've been able to map into the basin, but those didn't really compensate for the amount of evaporation that was going on in these warm tropical regions. So in that case, what would happen is that the water would evaporate out of the basin, the salinity would increase, and eventually you get to the point where you start precipitating salts, and then finally the potash deposits. This is just a standard structural contour map using all the well data that we have from, these are thousands of oil and gas wells that have been drilled through the state of Michigan historically over the last 125 years or so. And the purple contours are down around 8,000, 9,000 feet. And then as you get up into those greens, it gets shallower. And toward the edge of the basin, that same formation is only a few thousand feet deep. But just to give you a perspective on the geological data set that we have, all of the yellow circles on the wells there are wells that we have cores from. And we're lucky in this particular case, there was lots of exploration. So we have quite a few cores that have drilled through this interval, and we can actually get samples of the geologic deposits. This is a map of the cores. those dark areas across the top, that long band and toward the south, are actually oil and gas wells that have been drilled into the reefs. The reefs actually turn out to be really good oil and gas reservoirs, and we've produced almost 1 billion barrels equivalent of oil and gas from something like 1,200 different oil and gas fields in that particular formation. And that's the geologic formation right under the salt deposits. So it formed the framework on which the salt was eventually deposited. Historically, people have actually known about this potash deposit here in Michigan for quite a long time. Back in the 1950s, Dow Chemical, who came to Michigan in the 1800s to extract minerals out of the brine, were drilling wells all over the place. And they drilled a well in the late 1950s and didn't get around to studying it much until the 1960s, but it was called the Dow Chemical number 8 well. It was over in Midland County. That big bay that comes in from Lake Huron, it's called Saginaw Bay, and it was quite near that. You can see the arrow on the right is this particular well. And several of the geologists, Dave Matthews and several of his colleagues over in Dow Chemical, started looking at this core and noticed that there were some different chemistries in some of the salt. Most of the salt was sodium chloride, but in a few zones, they had a pretty extensive interval of potassium chloride. And obviously, even back then, they knew that potash was an important, valuable natural resource. That particular well, that Dow Chemical 8 well, they just drilled it and cored it. They didn't actually run any kinds of logs or any technical data, but there was a well not very far away, and it had a gamma ray log. Well, it turns out because potassium or potash has a radioactive isotope to it, it makes the gamma ray pretty distinctive. And so every time you have an accumulation of potash in a well, if you run a gamma ray log, you'll get a high spike in that. And so they compared the core that they drilled in that Dow salt well to a well called the Burton Emery well number 1. And the gamma ray log and the core analysis just directly overlapped each other. So they knew that not only could they use this core to assess the potash, but they could go around the state and map it and see how many wells they could see that gamma ray signature. And we still do that today. We've actually worked on a project in the last couple of years where we've digitized over 500 gamma ray logs throughout the basin, and gives us a really good ability to map the distribution of this potash deposit. So here's kind of a generalized map. Again, just focusing in on the north half of the state now. You can see that big black band is part of the that northern Pinnacle Reef trend that they produced all the oil and gas out of. But just in front of that, and then out into the center of the basin, you can see a number of wells, and all of these we've got gamma ray logs in, so we're able to assess the potash concentration based on the gamma ray logs. But in addition, we have all of those yellow circles, which are cored wells. When Mosaic and several of its associated companies were exploring in the late 1980s and early 1990s, they cored, I think we have 77 different wells that are cored through the entire Salina A1 evaporite unit. So we've got 15,000 feet of salt core that we can do some real detailed assessments of all of these potash zones. These are all the wells that we have gamma ray logs in. You can see it's pretty extensive throughout the whole northern half of the state. And based on that, we can make isolith maps of the potash intervals and get a real good detail about how this reservoir is defined. So it turns out this is just a close-up view of a well with the gamma ray log, and this is a neutron density and photoelectric log over here, typical oil and gas type well log suite. And you can see the spikes on the gamma ray logs, and there's actually 2 zones in the middle and upper part of the Salina A1 salt formation. The upper zone is a pretty continuous bed of almost solid potash that's about anywhere from 20 to 30 feet thick. And that's actually the target zone for most of the commercial mining that's happened here in the state of Michigan. Below that is a somewhat discontinuous zone of about 150 feet, of which the net amount of potash is probably 70 or 80 feet. So it's about 50% potash, which is still pretty high grade. And we'll talk about the geochemical analyses that we've done on these rocks in a few minutes, just to give us some quantitative numbers here. But this is kind of the way you can define these by looking at well log data. So you can get some remote data to give you some pretty good accuracy. If we just do a cross section across the upper part of the state now, where that previous map was, you can see how those zones can be correlated throughout the upper part of the Salina-Silurian interval. You can see the thicker gamma ray zone, particularly on the two left wells, for that zone called the Borgen bed. And then those basin-centered beds are much more extensive, and probably through much of the state, they would actually be the commercial target. So as Aaron mentioned, I'm here at Western Michigan University as part of the Michigan Geological Survey, and we have a core repository. We have around 600,000 feet of core from oil and gas, mineral, and various geotechnical wells in our repository. And so we have access to be able to look at these samples on a regular basis and do lots of research projects. And we're a public institution, and certainly available if anyone has a unquenchable thirst to spend time looking at salt. We've got it here, and you're welcome to come and look at it as much as you'd like. So the story about this, how we got it, was really kind of interesting. I knew these wells had gotten drilled because I was tracking all of the subsurface geology activity that happens here in the state of Michigan over the years. But because of the way the regulations are structured here in Michigan, a lot of the mineral wells aren't required to publicly disclose what they see and find, and they can have long periods up to perhaps 10 years of confidentiality before any of that data becomes public. But in 2008, I had a call from a person that worked for Mosaic Corporation. She was a student intern, and it was in the fall, and she was about ready to head back to college. And so they had given her the task of figuring out what to do with this large collection. They had it stored in a building up near the mine, and they had decided they just didn't want to maintain that collection anymore. So she said if we wanted those cores, we could have them. And I thought, man, that's great. We're going to go get some rocks. And when I drove up there in my pickup truck, I figured I'll just throw these boxes in the back of the truck and drive home. It turned out that there were actually 77 wells in these boxes. Are 4-inch by 4-inch by 36-inch long, typical oil and gas core boxes. And that was almost 12,000 feet of core. And actually, they were sealed in plastic bags, which is great for salt. It doesn't deteriorate in our humid climate here. And they had started the coring back in the 80s, and nobody had opened those boxes since that time. So it was kind of a pristine geological collection, and we were able to actually get a commercial moving company to help us bring that and bring that to our laboratory here. So we do have all that material now, and it's still in really good condition. This is just a close-up of a couple little pieces of core showing something about the deformation or deposition of the way the salt occurs. And you can see the little scale on there is centimeter scale. So these are individual little layers of salt. And then on top of that layer is a little thin crust of either gypsum or anhydrite or maybe carbonate that marked a little break in the deposition. And I kind of view these almost like tree rings. I suspect that this is some sort of cyclic, perhaps even annual depositional patterns, maybe a climatic kind of pattern with the salt being deposited during the warm, hot summer months and the erosion or deposition during the cooler, wetter months may have created that boundary. So pretty interesting unit. This is a deposit that's right underneath the KCl. So KCl is the mineral formula for sylvite or potash. And in the layer right below that is where you see this sort of almost barb-like depositional patterns of the salt. So we were getting more or less continuous deposition of salt, and then sometimes something changed in the climate and it got even more evaporitic and we started making the potash deposits. There's an interesting aspect to these cores. These were all drilled using typical oil and gas type technology, and they drilled it with halite saturated brine because they don't want the wellbore to get dissolved out and have the hole too big during the drilling process. So they saturate the drilling fluid up to halite grade saturation. So that means when they cut a core, the outside surface of the core is essentially true to the diameter of the coring bit. But sylvite is more soluble than halite. So as the drilling fluids are passing along the surface of the core, it's dissolving the sylvite in the rock, but not the halite. And so what happens is if we've got a rock that's mixed with halite and sylvite in the same rock, the sylvite will be dissolved a little bit, so there'll be a little relief on the outside surface of the core. And that's what I remember from my days doing igneous and metamorphic petrology. We had these little diagrams that you could visually estimate the percentage of one mineral versus another. And that's exactly what the outside of this core looks like. And so depending on how much halite versus sylvite was in that core, you could actually make a visual estimate. And so I just started playing around with that a little bit. And I'll just give you a couple of quick examples of what we did. We also did actual geochemical analyses of these samples so we can get real values of what the chemistry is. Did a couple of different things. We took the core and split it down and maybe wound up with a little stick about 1/8 of the size of the core, sent that off to labs, and they did wet chemistry on that. And they were able to give us back the chemical analysis, whether it was halite or sylvite or some other kinds of minerals. We also, on the big slabs of core, the big pieces of core, we actually just use a Dremel tool and routed out a long section of the core. So we got a continuous sort of average measurement of what that, let's say that foot or a couple of feet of core might have had for its chemistry. And that powder then we sent off to ICP-MS and got real detailed elemental analysis data there as well. So we've done this for lots of wells, probably about 20 or 30 of the cores. We have detailed every couple of feet the geochemical data. Going back to the visual estimation here again, the salt is so translucent that if you put a fluorescent light behind it, the light will actually shine through it. So this is a 4-inch piece of core that has light behind it, and you can actually see all the bedding patterns. And so here we had halite and sylvite. I've marked those where it's sort of mixed. You see some light coming through where it's pretty much all halite. The halite's kind of dirty, so you don't see much light coming through it. And then you get into the pure sylvite zones and they're almost transparent. So I just, if this is a foot-long piece of core, I broke it down to individual inches, and whether it was 100% halite or 100% sylvite or 50-50, and then just estimated what the total amount of sylvite might be in this. And you can see the numbers there. The visual estimate actually comes out pretty close, within a couple percent of what the actual geochemical estimate is, because we did the powdered estimate on these as well using the Dremel tool and ICP-MS, and it's less than 3 or 4% difference in the actual chemistry. So visually, you can get a pretty good idea of what the mineral chemistry is. The reason is because this is a pure two-phase system. The only thing in this rock is either potassium chloride or sodium chloride. There's less than 0.5% of everything else. This is just a close-up of another piece of core showing the same kind of thing. Here, the sylvite zones are really pure. And again, it's in that, this is out in the basin-centered beds rather than that upper unit called the Borgen bed. But the same thing works here. And And when you look at the chemistry, it's about 37% sylvite, whereas the other one was over 50%, and that's a pretty high grade. As I mentioned, the world sort of uses K2O, the potassium as an oxide, a chemical oxide, rather than as chloride. And that's what you would see on your fertilizer packages. That's the percentage number is in K2O. So if we think about what's going on here in the northern part of the state of Michigan, back in the Silurian time, that's around 427 million years ago or so, we were sitting around a little bit south of the equator. We had the world ocean was all around us, but because of the growth of coral reefs in the underlying formations, the Niagara and Pinnacle Reef deposits, a bunch of carbonate sediment was being deposited, and it built up a big ring around this Michigan basin, which then provided a kind of a trap in a sense that as climate changed over periods of thousands or millions of years, sea level would go up and down. And sometimes the sea level would drop below the level of the coral reefs, and it blocked the interior of the basin off from the rest of the world ocean. Because of the climate and the evaporative processes that went on, you started getting lots of salt deposits. And eventually, at some times, it evaporated it down to almost total dryness, and that's when you started getting the potash deposits. This reef trend was kind of a barrier, a dam that kept the water pooled or ponded right here in the northern half of the state. The basin is actually a little bit asymmetrical, with the basin being a little deeper to the north and a little shallower to the south. So when the water was evaporating down, it actually just sort of pooled based on gravity and drained down into this region right up against that northern reef trend. The green box here is where I think you could have a thick enough deposits based on all the electric logs we've looked at and the cores that it could be commercially developed. The yellow box is actually probably the extent of where the potash deposits were forming. And if you have a differential value in the price, you could possibly mine out into that area as well. But where all of these yellow circles and wells are clustered is that's where the commercial mining area has been historically. And that's where most of our data is. You can see how many wells are in that region. So we're pretty confident that that part of the state, at least, and there's maybe a few 100,000 acres there. Inside that green box is over 2 million acres. So that's a huge amount of area that could potentially be mined historically through time. All righty. So kind of to bring things a little bit together for you guys, we have a period of time in Michigan's geologic history where the state was sitting close to the equator. We had a continental configuration and a depositional series of events that produced a little bit of a sealed basin. And as subsidence continued, that basin provided a place to collect water. And over time, with the climatic changes, we could get enough evaporation that we got salt deposition. Various kinds of salt. There's thousands of feet of halite salt in this basin. There's only a few hundred feet of the potash salt. So the climate never got quite severe that you had potash being made all the time. But at certain climatic periods, you did get some potash development. It's in this area in the north central part of the state, a couple million acres. So potentially there's a lot of opportunity. These are more or less continuous beds in the subsurface. So it would be possible to develop a significant mining operation in terms of these deposits. Stratigraphy, basically, there's two different intervals. There was always a lot of salt deposition going on during this time frame, but there was a couple of times when it appeared that more potash was being made. So the upper unit toward the top of the Salina A1 salt, it's called the Borgen bed. That's actually named from a well called the Borgen well. It's actually not right in that key area where we're looking at, but it's a little bit north of that, right up in front of the reef trend. And then out in the center of the basin, which is much more widespread, and this is actually much more typical of potash deposits in other places in the world, we see a number of thinner beds that are a few inches to a few feet thick, probably a total net footage thickness of maybe up to 60 or 70 feet thick over a couple 100-foot interval. The chemistry of these, and this is actually based on analytical data, mostly from ICP-MS, the sylvite concentration in the Borgen bed is roughly 50% net over that total of 30 feet or so. If you convert that to potassium oxide, that's roughly a 35% grade. So if you were to look on your bag, that would be 35 on your potash concentration. So that's as high as you can get pretty much for any kind of commercial fertilizer. In the basin center beds, it's a little bit lower than that, mainly because there's the ratio of salt to potash is a little bit higher. And so it's typically only about 44% or so sylvite, and then the rest is halite in the stratigraphic section, which translates to about 27-28% K2O. But if we look at what else is going on in the world, the commercial mining operations actually mine fairly low-grade potash by these standards. The Canadian potash is published at somewhere between 18 and 24% K2O. So there's a lot of salt in their rocks, not quite as much potash. Even our basin center beds, which I would consider a little bit lower grade, are still higher than that. The Utah stuff is pretty good, 24% on average. From New Mexico, it's quite variable. Sometimes they mine stuff as low as 8%, mostly in the 20% range. And then the Russian stuff is also in the 18 to 20% range. So I would consider this a world-class deposit simply because of the grade, the quality, the accessibility in terms of where this deposit is located. It's essentially right in the middle of the upper Midwest corn and soybean farming belt. You saw from that original map I had that the highest demands up to 11 tons per square mile. Those pixels on that map were in tons per square mile, and the highest red stuff was 11 tons of potash used per year per square mile. So being right here in the upper Midwest, it's close to the farms where people need it, and it's a domestic product that's part of the United States and would cut down on our dependency for foreign imports. So that's my story, and I'm sticking to it. Thank you, guys.
Thanks, Bill. I really appreciate that. Just a couple of quick notes for our attendees. We'll be dropping the link to the quiz in the chat momentarily, so watch for that if you're needing CEUs for New York State registration. And remember that you do need to be on for 50 minutes, so we'll have a little bit of a discussion here. If you have questions, also please drop those in the chat. I'll kind of go through those and read those out to Bill. I do know that we've had a couple of questions already dropped in the chat. We'll try to get back to those in just a minute. One of the big questions here is, Bill, could you talk about how much groundwater or water in general is going to be required for solution mining in potash?
So yes, and they've been working on this. There is a company right now that's picking up the leases and is trying to get a new mine started here in Michigan. They've been working through all the permitting agencies, and they've secured all the necessary permits. Michigan has, as probably most of you realize, a fairly significant freshwater resource here in the state. It's also something that we think a lot about. They'll be using thousands of gallons a day when they get started. Once the process is underway, they're recycling most of the water that they produce. So initially, there'll be a fairly significant usage of water, but then as they move through time, they'll be recycling probably somewhere between 70 and 90% of the water that they're using. So they'll be using some makeup water as they go along, but for the most part, it is a water-intensive, obviously a water-intensive activity, but the recycling aspect of things is going to manage that water quite a bit.
Question from John. He's asking if there's any chance that the Hersey mine will reopen.
So it is actually still working. they're mining salt. Compass Minerals bought the operation from Mosaic, but of those two crystallizers, only one of them is still there. So when Mosaic sold their interest, they also tore down their potash crystallizer. So they do produce halite, pretty large quantities of halite from that mine, but they don't have the ability to capture potash anymore. Most of that salt, by the way, goes into water softener salt, but it is
Oh,
food grade salt. When you're dissolving it and evaporating it and then reprecipitating it, it's really pure. So it's very high grade. It's medicinal. It's food grade quality salt that they produce all the time.
to follow up on that, do you have any idea? This is from Gabriel. Do you have any idea why Mosaic left that mine? What was was it economics
So they
or?
are the main one of the main Canadian operators, and they purchased or they created that mine. They actually built the mine there in Michigan, I think, to basically keep other people from being able to access the asset. And so in Michigan, if you hold the mineral rights, nobody else can use them. So they never really produced, they produce millions of tons a year out of their Canadian mines. But in Michigan, they never produced more than about 110, 120,000 tons in any one year. So it was really a pilot plant that they created here. And I guess they just felt that it wasn't worth their effort to do it. And then about the time they were leaving in 2013, there was a fairly significant glut of potash on the market. So the price had dropped significantly. You know, it's in the $1,000 to $1,200 range now. It was down to under $300 at one time. So it's probably an economic decision in that sense, but it costs a lot to transport potash anywhere you go. And so the farther away the source is from where you're using it, the more expensive it gets. So if we could redevelop that resource here within the upper Midwest, it would be a significant benefit to the farmers. Perhaps 50 to maybe up to $100, depending on tariff costs in terms of additional costs to bring imported potash in.
A question from Paul, kind of a two-part question. He asks about how mineral rights work with solution mining, especially with respect to how you know which areas have dissolved with respect to property lines or claim boundaries. And then a follow-up to that is, are there subsidence issues with deep solution mining?
They've never reported any in this particular case, although they didn't mine very large caverns. Most of the caverns were only about 300 feet across in these, so they were pretty small. And at those depths, there's actually, even though salt is pretty ductile, there's also a lot of carbonates and sandstones in the stratigraphic column above the salts. So at those depths, I don't think there's so much of a concern. In other places in Michigan where they've created salt caverns and done a lot of solution mining at 500 or 1,000 feet, there has been some surface disturbance in those shallower areas. But I think with this depth, it's probably not going to be a big deal.
Question from Michael asking how is KCl converted to potassium oxide? And follow-up, is the potash the source of KCl water softening pellets?
So K2O is actually just a device to market. They don't actually turn it into K2O. It's just that's the way it's represented chemically so that people get an idea of what the percentage is. But if you spread potash on your fields, you're spreading potassium chloride. And because it's a lot more soluble that way, I don't even know what potassium oxide would be, but
Right.
potassium as itself as a metallic mineral is very unstable. So you wouldn't want to have it just as a pure mineral. The chloride form is the most stable natural form, and that's the way they keep it. K2O is more of a marketing, or I don't know exactly how that came into being. Maybe somebody in the business could tell us.
I I would guess that it's probably used as oxide weight percents for sort of a fair comparison, because we tend, as geologists, we tend to like to report things as oxide percents for this
Right. It
potassium or
never
sodium.
actually becomes an oxide.
Yeah. But it's a good question, because if this isn't your area of expertise, I mean, you would want to know that. So always
Of
good to get that
course.
information out in front of people.
Yeah, and I
Question
always
from
think of it as potassium chloride because that's what the natural mineral is.
right. That's what sylvite is. Question from Andrew asking about regulations for chloride concentrations in the 20 to 30% of disposed wastewater from operations. You said you was going to recycle 70 to 90. So what are the regulations regarding
So
that
they have to
other?
have a brine disposal well also, and Michigan does regulate brine disposal wells, and they would likely be disposing back into some really deep formation. There's only a few subsurface formations that are permitted for brine disposal. Because of the oil and gas industry that's been around for over 100 years, there's a fairly well-established protocol and industry for brine disposal here in the state.
Just a quick note, if you haven't started to take that quiz yet, it is in the chat. I'm going to ask if Wendy would drop that in again because we've had several questions, so it'll make it a little easier to find the link to the quiz. And then I have a question for you, Bill. You know, one of the things that I noted when you showed just the extent and volume of potash in Michigan was that it's a really large resource, and I saw that the USGS re-added potash to the critical minerals draft list here in 2025. Um, do you know of any work that's being done by the survey using maybe Earth MRI or other state mapping funds to try to get a little more detail on the extent of some of the potash deposits?
Yes, we have, and that's how we were able to get all our digitized logs put together. We also have some funds available right now from USGS to do more elemental chemistry, and they're going to allow us to do another 200 samples. So we'll be able to get additional. I'd like to get some more from outside the area of commercial development right now, because pretty much all of the assay data that we have is right in that commercial area. So looking at the quality in other states, we don't really have a great idea of what the real mineral chemistry is there.
Okay.
So yeah,
And
certainly, and it's pretty easy to do. You just powder up some of that stuff, works great in ICP-MS. And the other thing is that because it's so pure, you just don't have a lot of other components that you even have to be concerned about. Magnesium and sulfur are really the only other two elements that we see any concentrations of. Once in a while, there's a little boron. We were hoping to see maybe some lithium or some of the other trace elements. But because these minerals are so pure and most of the salts don't incorporate trace elements into their crystal structure very much. So this deposit is really pretty much pure, 97.6 or higher in most of the chemical analyses is either sodium chloride or potassium chloride. And the rest of it's typically a magnesium chloride. The other interesting thing is
pretty
that
impressive.
most of the other commercial potash deposits in the world have more magnesium chloride in them. And Michigan's deposit has virtually no magnesium in it. We think that's because that as the evaporation process was going on and new seawater was coming into the interior of the basin from the oceans, it was passing through that carbonate bank, and most of that magnesium was getting extracted out and turned the rocks into dolomite. Because although you expect those carbonates to be mostly all limestone, pretty much everywhere around the basin, they're all dolomite. So we think that all the magnesium that would have normally been in this salt deposit got turned into dolomite before it ever got into the interior of the basin.
That's an interesting idea. Almost like a dolomitization in situ
It's a
sort of.
molecular sieve in nature,
Yeah,
pretty much.
yeah, that's a great way to put it. One last thing here before we log off. I saw really several bits of discussion in the chat about how gamma ray logs actually might work and might not work. And what I remember from my college geophys is that halite doesn't have much of a gamma signature at all.
Right,
Um,
nothing.
could you maybe just talk a little bit about how that actually works in these deposits and how that gamma signature is evolving or how it's being
Sure, it's
reflected?
because potassium has radioactive isotopes. Potassium 40 is the radioactive isotope. So all potassium elements on Earth have a certain amount of radioactivity. The quantity of those potassium atoms of the radioactive isotope would give you the amplitude of that gamma ray curve. Now you really need to calibrate it because gamma ray curves are sort of variable in the way they're calibrated. So it isn't an exact percentage, although people have tried to work on creating algorithms to do that. But it gives you at least a qualitative idea of what's going on. The other thing is that sylvite is one of the lowest density minerals there is. Normal halite's about 2.01 grams per cc density. Sylvite's only about 1.83. So you've got a big density difference as well. So even if you don't have a lot of confidence in the gamma ray log, if you look at the density log, you'll see a big difference there as well. So in porosity, it doesn't do you anything because it's all no porosity. And the photoelectric factor does deflect a little bit differently with potash as opposed to silver or halite. But I think the main differential or the main useful logs would be the gamma ray because of the density, because of the radioactivity. And then the bulk density log would work good because of the major difference in the density. 15 or 20% difference in density is pretty big.
It's very big. And then I see one last question here. We'll give John Salvino the last question. He asks if there are any locations in the world today where we can see KCl forming.
There are some small restricted areas around the margins of saline environments today, but you've really got to get the salinity super high. There are some very high saline sort of terrestrial lakes. Some of those really evaporitic lakes out in the western U.S., some of those have some potash in them. Potassium chloride is not the only potash mineral. We can have potassium sulfate is a natural mineral as well. And so some of these inland lakes, these restricted intrabasinal lakes out in the west, sometimes they won't have a lot of chloride in them, but they could have sulfate. And so you might see a potassium sulfate mineral. But it's not something you would see when there's any opportunity for normal or even slightly saline marine waters to get in. You have to evaporate more than 99% of all the water to get to the sylvite precipitation grade.
Okay. Well, I said that was going to be the last question. Then Ben dropped one more in the chat, and his question is really about we have a large quantity and high quality potash in Michigan. So what do you think the factors are to explain why we import so much potash when we have some good sources here?
Well, I think it's commercial for the most part. It's a pretty expensive operation to run a solution mining operation. This new company that's trying to develop it has estimated it's going to cost them well over $1 billion to set up the mine. They have been able to secure a significant amount of funding, and we're anticipating that it's going to happen here pretty soon. But yeah, it's a very expensive operation. And as long as it's just like a lot of other commodities that we have, wherever you can find the lowest price, that's typically where people are going to go for it. And until you can develop more localized sources or decide that you're willing to pay a little more for getting something local, then we're going to depend on imports for a lot of these kinds of things. And I think that's happened. That's not just true for potash. It's true for most of the commodities that we deal with, that wherever, if we can get it and it's the lowest price, that's probably where we're going to try to go. And it's cheaper. I mean, if you're doing an underground mine, you just have the cost of running those backhoes underground pretty much. And it's a lot different. The energy costs alone in pumping water down, pumping the brine back up, cooking off the water to crystallize the salts, and then pumping the brines back down. That's all a pretty big energy cost system. And those systems right now are probably running on natural gas for the most part.
Okay. Well, I sure do appreciate that. I did see John Johnston said there's always one more question. And John, there always is, but that is going to be our last question for the day. Bill, I really appreciate your time and your expertise. It was a fascinating talk. For those of you that haven't completed the quiz yet, we'll try to keep that open for a few hours. So make sure you get that completed today. And don't forget that you can take that quiz as many times as you need to until you get 4 of the 5 questions correct. I sure do
hope it's
appreciate
not
it.
too hard.
Yeah, I mean, it's got to be hard enough. And I think I reviewed it. I think you did a great job on that, Bill. One last thing to all of our attendees. If you think that you might like to give a lunch and earn, please reach out to me. We love to have people come and share their expertise with the rest of our attendees. With that, we'll say good afternoon.
Thank you.